So in this example problem, we're going to determine the moment of inertia with respect to a few different axes. So we're first going to find what is the moment of inertia about the x prime axis, okay, which is located at the centroid of our cross section here. So we have a rectangular cross section. Then the second part of the problem, we're going to determine what is the moment of inertia that about the base of our area, right, which we'll call I of x. All right, and then for the last part of the problem, we're going to determine what is the moment of inertia about the z prime axis, which is kind of coming out of our board here, of our page here. So we'll call that J O prime. Right. So those are our three variables that we're trying to solve for. So we'll just go one by one and define it. So we know the equation for Ix prime is going to be equal to the integral of our about our area of y of prime d squared dA. Alright, so in order to evaluate this integral, we need to know what the heck is dA. Alright, so if we look at our area, we can draw a rectangle, a small differential element. Okay. Alright, and that small differential element has a finite width, which is equal to just b. Alright, times an infinitesimal height or thickness. Alright, so in this case the thickness is d of y prime. Alright, so if we plug that in, what we'll end up getting is we'll have our integral will go from minus h over 2 to h over 2, which is the largest value of y prime, its maximum and its min. Alright, and then we'll still have y prime squared times b, which is just a constant, times dy prime. So we can say that I of x prime in this case will be b integral of minus h over 2 to h over 2 times y prime squared dy prime. So the integral of that would be b times y prime cubed over 3 from h over 2 to minus h over 2. If we plug in that, we'll get Ix prime is going to be equal to base times base divided by 3 times h over 2 cubed minus h over 2 cubed. H over 2 cubed is equal to h cubed over 8. So what we end up getting is we have base divided by 3 times the height is going to be cubed divided by 8 minus the height cubed divided by 8. So if we add those two together, we get h cubed over 4. And what we end up getting is we'll get the moment of inertia is equal to the base times the height cubed divided by 12. Right. So that's the moment of inertia for a rectangle about the centroidal axis. All right. So in the case of our second, we're asked the second question, part B. We're asked to determine what is our moment of inertia about xb. All right, so you want to know what is IXB. All right. So in order to determine what is IXB, is since it's not about the centroid, all right, what we can do is we can use the parallel axis theorem to solve this. All right, so since XB is parallel with X prime, we can use the parallel axis theorem and we can solve for IXB. So what we can say is that IXB, according to the parallel axis theorem, is equal to IX prime plus the area times of our box times the distance from the centroid of our area to X of B. Right? So IX prime we just solved for up here. So we know that IX prime is equal to the base times the height cubed divided by 12. We know that the area of our circle, of our rectangle, is just equal to the base times the height. All right, and then the only thing that's left is the distance dy, which is the distance from our xb to x prime. So that distance is equal to just h over 2. So we're just going to add h over 2 here. And we're going to square that. All right, so what we'll end up getting is we'll get the base times the height cubed over 12 plus the base times the height cubed over 4. All right, now if we find the common denominator here, it's 12. So we would get base times the height cubed plus 3 times the base times the height cubed. So 4 divided by 12 is just the same thing as 1/3. So we'd end up getting the base times the height cubed over 3 would be equal to the moment of inertia about the base of our or about axis xb. Right. So then the last part of the problem asks us to solve what would be our it asks us to solve for our J0 prime, which is the polar moment of inertia about the centroid. So we know that we can calculate the polar moment of inertia about the centroid using Ix prime plus Iy prime. So we already know Ix prime from part A. So the only thing we need to do here is we need to solve for Iy prime. So to solve for Iy prime, what we're going to do is we're going to draw another element. We know that Iy prime could be equal to the integral of x squared times dA. So we want to make sure we try to put everything in terms of x. So we want to write dA in terms of dx. So we're going to go back to our diagram here, and I'm going to draw another differential element, this time going along the vertical axis. Alright, and what we can say here is that dA is going to be equal to the height times dx. Right? So if we plug that in, you would get I of y prime is going to be equal to the integral of x squared times the height times dA. So the height is a constant, and the height times dx. So that's our dA term. And then we know that x goes from minus b over 2 to b over 2. Alright, so we can bring out the height because it's a constant, and then we're left with x squared dx as our integral. So if we integrate x squared dx, we'll get I of y prime is going to be equal to h times x cubed over 3 from and then the bounds of the integral, so we have to evaluate at b over 2 and at minus b over 2. So what we end up getting after we evaluate all that is we'll get hb cubed over 12. Right? So our polar moment of inertia about the centroid in this case would just be equal to I of x, which was the base times the height cubed divided by 12 plus the I of y prime, which we just solved for, which is equal to the height times the base cubed divided by 12. Alright, so in these problems, the main thing that you're doing is you take your equation and you need to define what is your differential element. Once you define your differential element, you can then substitute it in, and you should be able to get everything in terms of a single variable, and then you integrate across the entire area to solve for your moment of inertia. Once you have the moment of inertia about a centroid, you can calculate the moment of inertia about any of the axes that are parallel to that axis. So then you just have to use the parallel axis theorem, which you just have to plug in the area of your area times d of y, and then once you add that, you'll get the answer here. And then the last thing you'll get is that if you want to calculate the polar moment of inertia, it's really simple. You just need to calculate each of the moment of inertias about the x prime axis and the y prime axis, and then you'll get the moment of inertia. And you just add them together to find the polar moment of inertia. All right, so that concludes this example on determining moment of inertia is about the x prime, the centroid, ix prime and iy prime, polar moment of inertia, and the moment about an offset axis.